And I'm gonna tell you a little bit about how we actually do some of these variation-aware designs. Okay, so start off real quickly here with what our mission is and at INVECAS. And the reason I want to take you through, I'm not going to take you through all this, but basically I'm going to try to describe to you why we do what we do. So basically we provide leading-edge memories, okay, and hardware-proven yield and performance to enable first-right execution. Now, in terms of our mission statement, what I want to point out is that throughout our mission statement, we go back to this things like yield that talks specifically to the need for variation-aware design, okay? And we try to differentiate our circuits through innovation. And Aziz described some forms of these innovations. You need to be able to verify these innovations before you commit them to silicon. And so these innovations need the variation-aware design facilities before you commit them to hardware. So it's very important there as well. We basically do power performance optimized memories, memory compilers, and there's a wide variety of compilers that we offer at INVECAS. And we implement read and write assist features, similar to some of the things that Aziz was talking about, to enable you to go to very low voltages and hit some of these IoT markets as well. We also have complicated dual rail supplies that enable the peripheral logic to go to a much lower supply level. This introduces an additional level of complexity that needs to be addressed during the analysis phase. Okay? And then we also build in self-test engines so that we can actually verify that the hardware is doing what we expected when it gets to the tester platform. And we do this in 3 different technologies at this point in time for global foundries. They're 22 nanometer fully depleted SOI technologies, very interesting technology. I would encourage you all to take a look at it because it's a very unique technology. And then there's a 14 nanometer FinFET, and then we're developing 7 nanometer in the very near future. So once again, I'd like to point out that I'm not going to take you through our entire guiding principles here, but I just wanted to point out to you that in the highlighted red boxes here are specific points about what we feel our differentiation points are and how they specifically talk to the need for a variation-aware type of design tool. We talk about maximizing yield. We talk about analyzing these innovative circuits, and we need to be best of breed, so we use best of breed tools, okay? An additional thing is that from a resource perspective, we want to maximize the reuse of our designs, and when you do that, you want to make sure that the circuits that you're propagating to all those other pieces of IP are very strong in their foundation. So you want to spend the extra time and effort to make sure you get that core foundation design correct right up front. And so it's worth spending the extra time and energy to make sure those get right so you don't propagate a bad design, okay? So this chart just demonstrates some of the complexities associated with a dual rail supply. So on the left-hand axis, we have the bit cell voltage. So there's a separate rail applied to the bit cell. And on the horizontal axis is the voltage that's applied to the periphery of the memory. Typically, this is the same voltage that's also applied to the logic of the chip. And so the SRAM voltage, the SRAM bit cell itself has a minimum operating voltage that tends to be higher than the minimum operating voltage of the peripheral logic. So in order to enable these high-performance memories, these high-performance chips to minimize their power envelope, we want to enable them to drive their operating voltage, as low as possible, below the operating voltage, minimum operating voltage of the bit cell. And this creates a very large window of operation that we have to operate our memories in, and we have to look at all these different corners, so we need the tools to help us accelerate the amount of simulation we do across not only process voltage and temperature, but it's also the multiple voltage ranges of 2 different power supplies and how they play off each other. In some cases, these voltages can be The bit cell voltage can be higher than the memory, than the peripheral, but it can also be lower as well. So you have a positive differential voltage and negative differential voltage that you have to worry about. So let me talk a little bit more about why we focus on variation aware. Now, who out here worries about a 1 in a million problem, right? Typically, nobody worries about a 1 in a million problem in their day-to-day lives. But when we have a chip out there with 300 megabits of SRAM, guess what? You got 300 of those 1 in a million problems on every chip. So you do have to worry about it right up front. And I don't know how many people play Powerball, but just so you know, I didn't happen to pick 1 in 300 million just out of the air, but it turns out to be, that's the same odds you have of winning the Powerball, right? So you gotta win the Powerball in this case, you have to win the Powerball every time you want to build a good chip. So you don't want those odds. You don't want to play with those odds. So you really have to focus very heavily on very deep into the sigma curve. So you really do need very high sigma analysis. We also have a very intense drive towards performance, power, and area. Okay? So in order to win business, you have to press the boundaries. You have to provide specifications that are very attractive to your customers. That's how you win business. Okay? But that's not the only part of the picture. If you want to stay in business, you have to deliver, and you have to be able to deliver those yields at very high sigma values. Okay? And so you have this trade-off you're always trying to play with being as aggressive as you can to win business, yet conservative enough that you don't end up with a manufacturing yield problem, because then you'll be out of business. Okay? And in order to do this in a reasonable amount of time, you have to, you could go after Monte Carlo, but that's very cost prohibitive to get to those extreme sigma values. So we need a high sigma tool, and in this case, we've chosen to use Solido for that tool. Now, when you talk about these type of statistics, when you're talking about 1 in 300 million, it's very easy to get lost in the math. The nice thing about the Solido tool is it has a very innovative approach to, it's easy for someone like me who doesn't have a strong degree in statistics to understand how the tool works, okay, and actually verify that it is working the way I'd expect it to do. In terms of bonus features, it has more than just this high sigma capability. It gives you very good feedback in terms of what specific devices and parameters are actually driving your yield losses, and it enables you to focus in and optimize specifically on those particular devices. And whenever you do this analysis, it's all about impacting change on the design. How are you going to make your design better? And so in order to do that, you really do need to know not only what the yield is, but what is putting your yield out at that spot. And that's, we get some very valuable information in terms of which device is actually giving you that yield. Okay? They also have very nice queuing management, which when you're dealing with a lot of jobs, it's necessary. And we can do nice PVT sweeping and a really nice graphical user interface. So just really quickly, here's a snapshot from their tool. The nice thing about their tool is that it doesn't use any fancy math to actually calculate the sigma. It actually rolls the dice as many times as necessary. So it'll roll at 300 million times or 600 million times, whatever you need to get to that sigma value. The nice part about the tool is it basically does a two-step simulation. The first step is it runs just a statistic, just a random sampling, and then it uses the data from that sampling to calculate or build a model and then focus all of your simulations on the tail of your distribution where you're the most worried about. So, I don't want to necessarily get too much into what this picture is all about, but basically there's your general sampling is in the gray, and then the purple sampling is where it has determined these points are actually on the tail of the distribution. Now, how do you know it's picking the right model to pick the right points in the tail of the distribution? Well, what it does is it builds an ordered list of simulation points, and so it simulates the one that it thinks it's going to be the worst first, and then the next one second, and the next one third, and you can see on the next verification slide whether it's doing that correctly or not. I'll talk about that in a second briefly. But the important thing is that a normal way that you would do this without the tool is you would basically do a small number of samples using regular Monte Carlo, and then get a sigma value and project that or extrapolate that. And what you can see on the bottom part of this graph is on the horizontal axis is basically a measured parameter, and on the vertical axis is a sigma value. And if you were just to use regular Monte Carlo and extrapolate, you'd see that this curve is not actually straight. It's a curve. And if you were to do that extraction, you'd probably find out that you would have some error associated with it because things don't perform the same way out on the tail of the curve as they do across the flat spot of the curve. And so this would introduce error. That error would either come in the form of yield loss or pessimism in the design point, making you less competitive. So it's very important to have a tool that actually does the simulation of the points out in that regime where you're worried about it. This is the verification modeling. Basically, on the horizontal axis is the number, the ordered point, the simulation point, and on the vertical axis is the measured parameter. And you can see on the far left, the very first simulation is picking the worst case point that gives you some confidence that their model is correct. Okay, and as you move to the right, as long as you see a decreasing value in the parameter you're measuring, that means that the model is relatively correct in terms of picking the point. So now you know that those small number of samples that you're actually simulating are on the tail of the distribution. Very, very powerful. So with that, I'll close with that one.